Okay, here are the worked out solutions to the page 232 homework on the first derivative test. Number 17, sketch a graph of a function f of x whose derivative f prime of x is negative on the interval from 1 to 3 and positive everywhere else. Okay, so if it's positive everywhere else, that means we have the interval from negative infinity to 1 where the derivative is positive, and then the interval from 1 to 3 where the derivative is negative, and then the interval from 3 to infinity where the derivative is positive. Remember that if the derivative is positive, then the function is increasing. If the derivative is negative, the function is decreasing, and again, derivative positive, function increasing. So the function's going from increasing to decreasing to increasing. And the important points to keep in mind are x equals 1 and x equals 3. All right, so we can make something that looks like it's increasing until we get to x equals 1, and then it's decreasing until we get to x equals 3, and then it increases again. I'm going to do that a little bit better. Okay, so increasing till we get to 1, decreasing till we get to 3, and then increasing again, something like that. Another idea would be to make it increase, decrease, increase, and then put your 1 and 3 in place at the appropriate spots. Okie dokie. Next problem, 29. Find the critical points and the intervals on which the function is increasing or decreasing. Use the first derivative test to determine whether the critical point is local, min, max, or neither. Okay, so we need to start by finding our derivative. And the derivative of 1/3 x cubed would be x squared. The derivative of 3/2 x squared would be 3x. And the derivative of 2x would be 2, and the derivative of 4 would be 0. Now that's not going to be undefined anywhere, so we're just going to find where it equals 0. And I believe that one is factorable, so we can factor it into x plus 2 times x plus 1, set each factor equal to 0, and solve each one. And we get x equals -2, or x equals -1, and those are the critical points. So now let's make the intervals. So we have the interval from -infinity to -2, the interval from -2 to -1, and the interval from -1 to infinity. We want to see what the derivative is doing in each interval. So pick a number in the interval. Suppose I pick -3, and plug it into the derivative, and the best place to do that is right here into the factored form of the derivative. So if we take -3 and plug it in there, we get -3 plus 2 is negative. -3 plus 1 is negative. Negative times negative is positive. Okay, now let's look at the second interval and pick a number in there. We could probably pick -1.5. Plug it into the factored form. -1.5 plus 2 is positive. -1.5 plus 1 is negative. Positive times negative is negative. And then pick a number in the third interval. Maybe we pick 0. Plug it into the factored form of the derivative. 0 plus 2 is positive. 0 plus 1 is positive. Positive times positive is positive. So what does that tell us about f, the original function? The function goes from increasing to decreasing to increasing. Now, based on that, we can conclude that we have a maximum, a local maximum, at x equals -2. Because the function went from increasing to decreasing. And we can also conclude that we have a local minimum at x equals -1. Because the function went from decreasing to increasing. Okay. Problem 31. Same idea, different function. Let's find the derivative. We get 5x to the 4th plus 3x squared. There's no place where that's undefined, so let's just set it equal to 0 and solve for critical points. Let's start by factoring out x squared. So we have x squared times the quantity 5x squared plus 3 equals 0. Set each factor equal to 0 and solve each one. So for the first one, we square root and we get x equals 0. For the second one, 5x squared equals negative 3, x squared equals negative 3/5, x equals plus or minus the square root of negative 3/5. Well, those are imaginary numbers, and we're not dealing with imaginary numbers in calculus. We only want the real numbers, so those don't count as critical points. So the only critical point we got was x equals 0. So our intervals are going to be negative infinity to 0 and 0 to infinity. Let's see what the derivative is doing in each interval. So I'm going to pick a number in here. Suppose I pick negative 1, and I'm going to plug it into my factored form of my derivative. Negative 1 squared is positive, and negative 1 squared is positive, times 5 is positive, plus 3 is positive. Positive times positive is positive. And then I'm going to pick a number in the next interval. How about if I pick positive 1? Positive 1 squared is positive. Positive 1 squared times 5 plus 3 is positive. Positive times positive is positive. Okay, so this graph, f of x, or y, whatever we're calling it, y is going from increasing to increasing, so there are no local maxes or mins, no local extrema. All right, one more problem, 45.